Hi everyone, welcome to our talk for Fox 2020. My name is David Stalfa, and today I'll be presenting our paper on scheduling partially ordered jobs in the presence of communication delay. The title of our paper is Scheduling Precedence-Constrained Jobs on Related Machines with Communication Delay. My name is David Stalfa, and this is joint work with Biswaroop Maiti and Rajaraman at Northeastern University, Zoya Svitkina at Google, and Aravindan Vijayaraghavan at Northwestern. We're going to build up our full problem from simpler special cases. First, let's consider precedence-constrained scheduling. Here we're given a set of m machines and n partially ordered jobs. Each job has size PV. This gives the amount of time it takes a job to execute on any machine. If job U precedes job V, then U must complete before V can start in the schedule. And our goal is to schedule the jobs to minimize makespan, or the completion time of the last job to finish. There is a fairly simple approximation algorithm for this problem. Perform a list scheduling procedure in which at the completion of any job currently running, check to see if any other jobs are available, where a job is available if all of its predecessors have been completed. If there is an available job, place the job on some idle machine, and continue until no jobs are available or all machines are busy. If there aren't any available jobs, continue to the next completion time in the schedule. The figure gives an example of a schedule you might get from list scheduling. Job A has been placed at the start of the schedule, and once it's complete, we can start executing C and D, chosen arbitrarily. Once one of them finishes, we can execute B, and once B completes, we can execute E. This algorithm was shown by Graham to be a 2 approximation for precedence-constrained scheduling. Now let's take a look at a slightly more complicated problem, precedence-constrained scheduling on related machines. Here we're given m machines and n different sized jobs as before, but this time each machine I comes with a speed Si. The ordering is the same as before, preceding jobs must be completed before their successors, but in addition we have the requirement that the amount of time it takes job V to execute on machine I is given by the size of V divided by the speed of I, or PV over Si. The goal again is to minimize makespan. This problem requires a more complex solution. Janek and Schmoys were the first to give a logarithmic approximation for this problem, and we outline their algorithm here. First, we define the shown linear program. Variable C is meant to capture the makespan of the schedule, and SV is meant to capture the start time of job V. The variable XVI indicates whether or not job V is executed on machine I. Informally, the first constraint states that the makespan is greater than the completion time of any job. The second constraint states that the precedence order among jobs is obeyed. The third constraint states that the makespan is larger than the total load on any machine. And the fourth constraint states that all jobs must be entirely executed. The technical details of this program aren't really important here. What matters for our purposes is that the related machines problem can be captured with a fairly straightforward linear program. The algorithm solves this LP and rounds the solution to assign each job to a group of machines. It then performs list scheduling on the jobs, with the additional requirement that all jobs must be placed on some machine in the group to which they are assigned. The figure shows an example of a schedule you can get from group-based list scheduling, given an assignment of jobs to groups. In the figure, job A is assigned to group 1, where all machines have speed 1. Jobs B, C, and D are assigned to group 2, where all machines have speed 2. In the list scheduling procedure, A, C, and D are executed first on machines in their respective groups. Though A finishes earlier than either D or C, we must still wait for C to finish before starting B, because B must be scheduled on group 2. This algorithm yields a log-M approximation for precedence-constrained scheduling on related machines. Now let's move on to precedence-constrained scheduling on related machines with communication delay. Here we're given m machines with variable speed and n jobs with variable sizes as before. The time to complete a job on machine I is still PV over Si, and predecessors must still complete before their successors can start. However, now we have an additional condition that if U precedes V and they are executed on different machines, then there must be at least row time between the completion of U and the start of V. Intuitively, this is the time it takes to communicate the result of U to the other machine where we're executing V. If U and V are executing on the same machine, then V can start immediately after U. Again, our goal is to minimize makespan. The two situations arising from communication delay are shown in the picture. On the left, we see that if B is scheduled on the same machine as A, then it can start its execution immediately after A. On the right, we see that if B is scheduled on a different machine from A, then it must wait at least row time before starting its execution. As far as we know, there are no prior results for this particular model, though several recent results have made progress on special cases. Our main results concern a model which allows the duplication of jobs. A job is duplicated if it is executed on multiple machines. And this capability can be helpful when scheduling with communication delays, as we see in the figure. On the left, we see a schedule of A, B, and C without duplication. Here we must execute A first, and then can schedule B immediately after on the same machine. However, we must either wait until B is completed before scheduling C on the same machine, or wait row time to schedule C on a different machine. On the other hand, if we are allowed duplication, as on the right, we can execute A on two machines and then schedule B and C immediately, each after one copy of A. As far as we know, there are also no prior results in this model either, although again, some results have been shown for special cases. We motivate our model with an example from machine learning. In deep learning, we often want to process many jobs represented as large bags. In order to process these jobs quickly, we might utilize multiple kinds of processors, GPUs, CPUs, DPUs, etc. Our model arises from the different capabilities of each processor, modeled as machine speed, the distance between processors, modeled as communication delay, and the dependencies among the jobs, modeled as precedence ordering. This problem is generally known as device placement. Here we review some prior work on scheduling on related machines and scheduling with communication delay. For related machines, the current best approximation is a log m over log m approximation due to Shi-Li, which improves the log m approximation from Dirac-Moyse. The central component of the algorithm in both cases is a linear programming relaxation of the problem and a grouping of machines by speed. The problem is also known to be hard to approximate to within a constant factor, though which factor depends on complexity theory assumptions. For scheduling with communication delay, utilizing duplication was first proposed by Papadimitriou and Yannikakis. For finite machines, the only approximation result is an asymptotic approximation due to Lapeyre and Rapin, upon whose work we build here. In the no duplication setting, several recent results have made use of the Shirali-Adams hierarchy. One such result is a QP test for O1 identical machines and O1 variable delay by Kulkarni and Tarnowski. Also, an independent paper by Davies, Kulkarni, Rothwas, Tarnowski, and Zhang, which appears in this session, presents a log rho log m approximation for identical machines with fixed delays. For our work, the central guiding question is, can we design polylogarithmic approximation algorithms for scheduling precedence-constrained jobs on related machines with communication delay? Our main theorem provides a partial affirmative answer to this question. We show that given an instance of precedence-constrained scheduling on m machines with delay rho, we can compute a schedule whose makespan is within a log m times log rho over log rho factor of opt plus rho when duplication is allowed. We show this result using a linear programming relaxation that builds on the one given in the related machines algorithm above, although we include several new non-trivial constraints to capture communication delay and duplication. As above, we use a solution to our LP to assign jobs to groups of machines. We then run a scheduling procedure which carefully balances the benefits of duplication against the drawbacks of duplicating so much that we overload the system. We discuss this algorithm in more detail below, and full details are in the paper. We note that if opt is at least rho, that is, if opt has any communication at all, then our algorithm provides a true approximation for this problem. Our next main result concerns the linear program used in our Makespan algorithm. We show that for a family of instances, the linear program has an integrality gap of at least omega square root log rho, where rho is at least some sufficiently large constant. The proof of this theorem uses graph expanders and shows an interesting property of random graphs after edges have been removed. Basically, after removing edges, the graph is no longer random, but we show that we can still exploit certain properties of the original randomness to derive the theorem. We call this property robust expansion, and it serves as the basis for our integrality gap result. This theorem serves as the first evidence that constant approximation guarantees may not be tractable with known techniques. Our third and final result concerns the benefits that duplication affords. We show that for any schedule that uses duplication, we can convert it into a schedule on the same instance that does not use duplication, and we incur only a log squared n log m factor increase in the makespan. The main technique in proving this result is a ball-growing algorithm that selects jobs that are then iteratively scheduled in successive rounds. An interesting corollary to this theorem is that, coupled with our algorithm for makespan for duplication, we can actually give a polylogarithmic approximation for scheduling without duplication. We now cover a main algorithm for makespan with duplication. One central component of our algorithm is a linear program relaxation. One main challenge in formulating this program is capturing the communication delay constraints in the presence of non-uniform job sizes, non-uniform speeds, and job duplication. One intuitive approach is to define an indicator that tells you when two jobs are executed on the same machine. Another approach would be to define an indicator to tell you when two jobs are executed within a communication phase of each other. However, each of these approaches has problems. The first can be made feasible without any consideration of communication delay, and the second works well in the setting of unit speeds and unit job sizes, but fails when the speeds or job sizes are variable. These failed approaches motivate the more complicated program we present next. Our relaxation builds on the LP for related machines, but introduces new variables and includes two new non-trivial constraints. Our new indicator variable, ZUVI, tells you if two jobs, U and V, are scheduled within row steps of each other on a machine no faster than I. This relies on an ordering of the machines from slowest to fastest. The first new constraint is the communication constraint. Recall that SV gives the start time of job V, and XVI indicates whether or not job V is executed on machine I. Informally, the communication constraint states that for job U preceding job V, V must start at least row units after the start of job U, unless there is some copy of U scheduled on the same machine as V. Note that this constraint is more permissive as the value of the Z variables goes up. That is, the more we duplicate, the earlier we can schedule jobs. Second, duplication constraint states that the total size of all of these predecessors that can be duplicated in the row steps prior to executing V on machine I is at most rho times SI. Intuitively, all these duplicated jobs would have to be executed on the same machine as V within row time of the start of V. Note that this constraint is more permissive as the value of the Z variables goes down. In this way, the LP itself balances the benefits of duplication with the drawbacks of increased load. Our algorithm consists of 4 subroutines outlined here. The first subroutine removes any machines that are too slow to be useful. This is a standard step in scheduling on related machines. The second subroutine solves the linear program given above. The third subroutine takes this solution and uses it to assign jobs to groups of machines, where machines are grouped based on their speed. This assignment just uses the values of the X variables and is the same as the one used for related machines above. Finally, we have our scheduling subroutine, in which we must carefully balance the trade-offs afforded by duplication. Our scheduling subroutine iteratively schedules any jobs that satisfy the 3 conditions shown. When scheduling a job V on a machine I in V's group, we require that all of V's predecessors fit in a single communication phase on I, are assigned to groups faster than I's group, and have some fraction of jobs not previously scheduled. We iteratively schedule jobs until no jobs meet these conditions. At this point, we insert a communication phase into the schedule to communicate the results of all completed jobs to all machines, and then we iterate. To analyze our algorithm, we first divide the resulting schedule into phases of length of row. We also define a chain of precedence-ordered jobs that each take a sufficiently long time in the schedule. We then partition the phases into three types. In load phases, all machines in some group are busy for at least half the time in the phase. This is shown in the right-hand portion of the figure, with the group consisting of machines 4 and 5. In chain phases, some job in the chain is executed for at least half the time in the phase. This is shown in the center part of the figure, where dark gray jobs indicate chain jobs. Finally, height phases are all the remaining phases. That is, the phases where all groups have some machine busy for less than half the time in the phase, and where no chain job is being executed for at least half the time. Bounding the number of each phase type yields the final upper bound. We now briefly overview our results on duplication advantage. Here we see an instance which provides a lower bound on the benefit of duplication in the presence of communication delay. On the left, we see an optimal schedule with duplication. Here we can schedule each path in the tree from root to leaf on a separate machine and complete the entire graph in row time. The figure on the right depicts the optimal schedule without duplication. Here we have to schedule the root node on a single machine along with some of its predecessors. We can then communicate the result of this group to all other machines and recurse on the subtrees. This procedure takes omega rho squared over log rho time. This tells us that duplication can reduce the makespan by about a factor of rho, log m, or log n. The main result is an upper bound on the benefits of duplication. We show that we can convert a schedule with duplication on n jobs and n machines to one without duplication and incur only a log squared n log m factor increase in the makespan. The conversion algorithm divides the schedule into phases and groups jobs within a phase by how many times they're duplicated. We then focus on those sync jobs without any successors in the phase and build a graph over them where two jobs share an edge if they share a common predecessor. We then employ a ball-growing subroutine to group these jobs into regions of diameter log n and assign each region to a single machine. The theorem yields an interesting and surprising corollary. Combined with our Makespan algorithm, the theorem yields an approximation algorithm for Makespan when duplication is not allowed. The reasoning is briefly presented here. Basically, when opt is less than rho, there can be no communication, so all connected components in the DAG must be scheduled on a single machine. These components can be list scheduled to achieve a 2 approximation. On the other hand, if opt is greater than rho, then we apply our Makespan algorithm and get an asymptotic approximation when duplication is allowed, which we then convert to a schedule without duplication via the theorem. Since opt with duplication is less than opt without duplication, this yields a true approximation for the case without duplication. Finally, we present some open problems for future research. The first is the question of whether or not the approximation factors given in the paper can be improved, either through alterations to the algorithm or to the analysis. The second is the question of little omega 1 hardness for the problem, which we were not able to prove. It would also be interesting to prove tight bounds on the size of the gap between the upper and lower bounds for duplication advantage. Another question is whether we can eliminate the asymptotic approximation from Makespan with duplication and achieve a true approximation. Finally, there's the problem of generalizing our results to a wider class of communication delays, such as metric delays or a delay hierarchy. Thank you for listening to our talk. We look forward to hearing your questions at the conference.